have the banquet, as far as I understand.
Exactly.
So yes, please, Andrei.
Okay, dear colleagues, dear guests, dear participants, it's my great pleasure to introduce our today's guest, Professor Emanuel Gull from the University of Michigan, United States. Let me say a few words about his scientific career. He graduated from ETH Zurich, Switzerland, and then started his PhD studies in the group of Professor Matthias Troyer. He graduated in 2008 and then moved to Columbia for postdoc and spent 3 years in the Department of Physics of Columbia University. After that, he worked a half a year at the Max Planck Institute for Complex Systems in Dresden from 2019 to 2011. And no, in 2012 for half a year, sorry. And then he moved to Michigan in 2012, and since then he's working as a professor and leading the group of condensed matter theory. Let me say a few words. He is known in particular for development of continuous time Monte Carlo methodology for quantum impurity models and key contributions to the ALPS open source software library for strongly correlated electron systems. He has got several awards and distinctions, and among them, I would like to mention the Neville Mott Strongly Correlated Electron Systems Prize in 2013 for a person who has made distinguished contributions to the theory of strongly correlated electron systems. Recently, Professor Gull obtained the ERC Advanced Research Grant and is going to move to the University of Warsaw and work there and in a research group and lead the research activity in the next 5 years or more. Please, Emmanuel, I'm very happy to pass the microphone to you. The floor is yours.
All right, thank you very much, and thank you for the invitation. So this talk will have nothing to do with continuous time methodology, and it will also have nothing to do with the ALPS library, though everything that I'm presenting is actually available as open source in various software packages. And if you go to the various references that we have here, you will find links to source codes that you can play with and computer software. As was just mentioned, I'm actually moving to Warsaw for the next 5 years to work on an ERC Advanced. Title is Quantum Algorithms. And what we're going to do in that talk is pretty much the same type of physics that I'll present in this presentation. We're going to work on various aspects of condensed matter theory, making condensed matter theory concepts work for realistic systems. And that will have aspects of, traditional analytic theory, high performance computing, diagrammatic field theories, quantum physics, and all of these things. All right, here's my group. I'm in particular going to talk about work that Johnny Fay has been doing and work that John Anier and Sergei Skakov have been presenting. So let me take a step back, and when we talk about computation of quantum systems, and especially not of lattice model systems, but of realistic interacting solids, what is it really that we can do well? And as you all know, right, I mean, since the beginning of computation, we have been developing computer codes that can develop tools for electronic structure problems. Density functional theory these days is really the workhorse of electronic structure theory, and there's a lot of stuff that works really nicely in density functional theory. For example, ground state lattice structures, phonons, behavior of solids with light elements, basically anything chemistry, Fermi surfaces, band structures, or the occupied part of band structures of simple solids, and so on. And almost as importantly, the barrier of using density functional codes is actually very low. So there are numerous open source software packages that one can go and download, that undergraduate students even can go and download, where they can enter the lattice geometry of the solid that they want to study, relax the geometry, and get usually reasonable results for typical solids. So no deep theoretical or computational knowledge is needed for that. That's very good, but very often if you go down to the basement and you actually ask the experimentalists what they're interested in, that is not what we can calculate with these codes. So very often we have strong electron correlation, d electron materials or f electron materials. Generically, I'll call them here quantum materials. Those are materials with narrow bands where correlations are important and density functional theory is often inaccurate. We're often interested at finite temperature. We're interested in phase transitions, especially electronic phase transitions. We would like to simulate what you measure in optics, for example, ARPES, Raman, Rix conductivities, or second harmonic generation. We'd like to look at transport, right? We like to look at time-dependent behavior. And at the end of the day, we'd like to go down the hall to our analytic theorists and talk to them in the same language that they are thinking about when they're looking at solids. And very often that is not the language of ground state densities. Similarly, there's an applied mathematics perspective on this field, which is that when you have a calculation, you want to be able to show everybody that the calculation is right or accurate, and that it's right for the right reason. And for that, we would like to have not just a calculation, but some sort of error estimate or error bar on the results that we're getting. We'd like to know that if a calculation is not as good as we want it to be, that there's a way of adaptively refining that calculation to make it more and more accurate. There has to be a rigorous way of estimating uncertainties, and ideally we want to have theories that have no adjustable or no free parameters that we can use to tune them to get whatever we're expecting from experiment. And this is not a new concept. You see here a quote of Paul Dirac, who says, "It therefore becomes desirable that approximate practical methods of applying quantum mechanics should be developed, which can lead to an explanation of the main features of complex atomic systems." And he finishes the sentence with, "without too much computation." And basically that's going to be the program of today. The theoretical framework that I'll use for this is the framework of quantum field theory. And for that, I just, I want to consider an electron propagating through a solid. Every now and then, it will bump into another electron and it will interact with that electron. We know how this interaction works. That's just the Coulomb law. And if we start summing up all of these processes of electrons propagating and bumping into each other, we end up with, here diagrammatic quantum field theory. In this particular case, the interaction lines that I have that signify the Coulomb law are described by the wiggly lines, and the propagators are described by the bold lines that I have over here. And in principle, we can now write down all of these possible interactions. Ideally, as we go up in order, the contribution of this interaction will, very quickly decrease, and then we can enumerate them one by one, draw pictures, and get a result. And really, that is the framework of diagrammatic field theory of the 1960s. It's very straightforward in textbooks, and when it works well if you have a small parameter, but when there are many electrons and complex, entangled or correlated processes, these simple pictures are often not sufficient, but the generic underlying formalism of finite temperature field theory and statistical mechanics, of course, remains valid and directly contains what we have here in the theory to the experiment. So for example, the propagator that I've drawn over here, the single particle electron propagator, is very closely related to what you would typically measure in an angled result photoemission spectroscopy experiment. So as I said, that's just the 1960s stuff. If you go and look a little bit closer, then you find that there are all sorts of diagrammatic theories that you could in principle talk about. You could talk about Baire expansions or lower order expansions, for example, non-self-consistent second order perturbation theory. In the field, this is called MP2. You could recite that certain fluctuations are very important and you're going to sum them up in a geometric series. That's the random phase approximation in electronic structure. It goes under the name GW, but really that's basically the same. In superconductivity, we would talk about ladder diagrams. So this is basically the same, but additionally we capture certain fluctuations. We can look at conserving theories, phi-derivable theories, or possibly psi-derivable theories, where in addition to having fluctuations, we may additionally also satisfy certain conservation laws. If we're interested in finite temperature phenomena, then thermodynamic consistency is very important. We want to have a starting point independence, and so on. That requires you to go to self-consistent theories, feed propagators and interaction diagrams back into each other and self-consistently converge the theory. And finally, we can decide that certain parts of our quantum system are very complex and very important. And so we want to take them out and do them at a higher order of theory than the rest in there. And that leads you to the formulation of embedding theories. With that, you have perturbative and non-perturbative parts, and you can see that you can gradually sort of ramp up the difficulty and the complexity of these diagrammatic theories. All of these theories you can write down in various ways. You can do it on a real frequency axis. You can do it in finite temperature, Matsubara formalism. You can do it in real time and look at pump-probe experiments. And you can do all sorts of diagrammatic languages. So I just showed you an interaction expansion where we had, diagrams were simple if we had few Coulomb interactions, but similarly, you can do hopping expansions, you can do other types of expansions. And so all of this leads you to I would say, very well-established zoo of diagrammatic perturbation theories that one could in principle look at for understanding interacting solids. Now, when we do that in practice, often the types of decisions that we have to do about which theory we want to take are not just motivated by all the theories are out there, but also, the sort of practical implementations that we would have to do to get to numbers from a theory. The natural route of doing all of this is to not even use diagrammatic perturbation theory and just use density functional theory. And I'm just simply not going to talk about this. Great method. We understand its limitations, and it has very many strengths. So if we then go the diagrammatic route, we could in principle do low order perturbative simulations. And, MP2, second order perturbation theory of a solid or something like that. And there we find immediately that there's a lack of fluctuations and screening. For metal, often these things don't even converge. And so it's not something that I'm going to talk about more, but MP2 certainly is something that one could in principle do for solids with large band gaps. We could try to do a single shot perturbation theory. So for example, we solve a system with density functional theory, and then we extract propagators from density functional theory, and we try to do some diagrammatic theory on top of that. That in principle works reasonably well. And in fact, most of the so-called GW calculations that you find out in the wild are actually based on a single shot on top of a density functional theory solution. And that really works reasonably well. Whatever density functional theory works well, for example, semiconductors, typically that works, quite well. But for the more strongly correlated systems that we're interested in, where density functional theory is not a good starting point, and that's really the reason why we're doing all of this in the first place, that's basically game over here because we can't systematically improve this. And so that means that we have to go to these self-consistent, conserving and consistent approximations, the phi-derivable theories or psi-derivable theories. And there, too, we can solve these in various ways. We can try to solve this for real frequency problems for the ground state. And it turns out that this is theoretically very appealing. But if you're practically trying to solve a real frequency self-consistency, this is very, very difficult to do. And shifting the poles that occur in these theories is, technically very demanding. And so it's not something that the field has managed to do successfully. We could try to do this in real time and with Keldysh diagrammatics. And that actually turns out to be really interesting. It is something that requires time evolution, but it's also something that offers you to look at time-dependent phenomena. So if you have a system, a quantum system that sort of sits there in its ground state and you start blasting it with a laser pulse, it will then, start having excitations. Those excitations will propagate. If you have a mechanism, they will eventually decay. And so that allows you to look at, for example, pump-probe spectroscopy. But of course, it's a two-time formalism. It's technically very demanding to do this. And so we know how to do this for atoms and small molecules. But to try and do this for a realistic solid is really something that is, very, very difficult. Which basically leaves us with finite temperature field theory, or the imaginary time or Matsubara formalism of quantum statistical mechanics. In that formalism, energetics and thermodynamics are basically built in, and it comes out very nicely by construction. A lot of the sum rules, a lot of the thermodynamic relations are just intrinsically fulfilled. It's also straightforward to integrate, embedding theories, such as, for example, the self-energy embedding theory or the dynamical mean field theory, into these formalisms, because they're already formulated as a field theory with an action. And so embedding certain orbitals into other orbitals is actually something that is very natural and very straightforward. The problem with finite temperature field theories is that at the end of the day, we would like to talk to experiment. An experiment often talks about response functions, speckle functions, gap functions, susceptibilities that are measured on the real frequency axis, and so on. And within that formalism that is working on the Matsubara axis, extracting gaps in single and two-particle spectral functions requires analytic continuation. And that analytic continuation introduces a lot of uncertainty into the process and really has been a stumbling block in using finite temperature field theories successfully for realistic systems. But let me take a step back, right? After all, this was done in the 1960s. And so what really is new here? Why wasn't this done for realistic systems back, in the 1970s? And it turns out that when you're thinking about this a little bit more, doing a diagrammatic field theory for an actual solid is remarkably non-trivial. We're talking about finite temperature formalism, the Matsubara formalism. Well, now you have a realistic solid. The energy scales of the realistic solid are typically in Hartree. The temperature scales that we care about are, 300 Kelvin for the equilibrium temperature. But if we want to, resolve competing phases, we're really talking about a 1 Kelvin difference. And so if you do the quick calculation, you see that just to resolve a propagator, a non-interacting Green's function in this formalism requires you to consider billions of Matsubara frequencies and use gigabytes of data. The interaction tensor is just the same. You see the interaction tensor down here. This was the wiggly line that I had in my diagram before. This is a rank 4 tensor where the indices consist of 4 orbital indices, or if you're doing it in a solid, 3 momenta and 4 orbital indices. And so even if you use only like 120 orbitals per unit cell, which is about the minimum you could get away with, and you put this on a 4x4x4 grid, just writing down the Coulomb interaction takes you 405 terabytes of storage. And at that point, you haven't even done any calculations with it. That's just writing down the object. And so you see that, naively, you're not talking about a G and a U the way that you write this on a blackboard for a Hubbard model. But, these are massive objects. And a lot of the limitations of doing this realistically for large systems, came from, having to be able to handle these objects in practice. And so there's I would say a remarkable behind the scene technical and numerical work over the last couple of years, maybe the last decade, that has enabled us to take these objects, compress them, and adaptively work with them in such a way that we can now do field theories kosher and really manipulate these diagrams and compute, contract interactions with propagators and so on. A big part of what has enabled this are GPUs and what nowadays is called artificial intelligence and machine learning sort of infrastructure. If you look at that second order diagram that I wrote up there, it consists of 3 lines and 3 straight lines and 2 wiggly lines. That's a contraction of 3 Green's function with 2 Coulomb matrix elements. And so if you look at this, that's basically just a bunch of tensor contractions. And tensor cores or tensor matrix infrastructure on our modern GPUs is very efficient at handling these objects. If you think of a typical high-end GPU, high-end CPU, you get about a 1 teraflop per second. So that's 1,000 billion operations per second of add, multiply, subtract, or divide. It costs about $4,000 and it has about, somewhere between 20 and 128 cores or so. But that's about the performance you're getting out of one of these. Even a couple of years ago, out of a Volta GPU that you see displayed here, you get about 6 teraflops per second of GPU performance, and you get about 8 of these cards per node in a supercomputer. And then, of course, entire racks of nodes stacked, and then hallways of racks forward and back, of these GPUs together that allow you to have the computational muscle to do these calculations. GPU computing infrastructure is one of the fields of hardware engineering where the field is making enormous progress. A couple of years ago, we were talking about 6 teraflops per second. Nowadays, we are, I think 163 is the newest AMD core, on the order of 100 teraflops per second of just sheer algorithmic computational muscle of add, subtract, and multiply that allows us to do tensor contractions very, very efficiently. And with that, go back and take the theories of the 1960s and really run them for interesting applications.
Emanuel, may I ask a question?
Sure.
So, did you hear about TPU, tensor processing units?
Yes.
Are they convenient for these purposes or not?
They are very good for these purposes. And in fact, what we do here for most of these operations are so-called batched matrix multiplies, batched gems, in our case, Z-gems, so double precision complex multiplies. Typically, this stuff is in imaginary time with adaptive compression. We have maybe about 200 or so or 300 matrix multiplies that we can do in parallel, and we just simply dispatch this on the GPU. And the GPU dispatcher then will place some of these on tensor cores, others on the normal cores, and will basically run at close to peak efficiency. We have that over here, actually. Now, this is the generation just before the tensor cores, right? But you can see here that when NVIDIA sells you a GPU, they give you a number like 6 teraflops for this particular GPU per node. And we are getting close to 72% of actual peak flop. That's basically unheard of. I mean, a usual, CPU code runs at, close to 10% if you're really good at, peak flop. Here we're reaching really very, very close to the absolute maximum that these cores can do. Because these tensor contractions are so well parallelizable, we can use a large number of GPUs. And with that, the time that we spend per iteration on these GPUs goes massively down. And that now allows us to do very many of these self-consistent iterations that we need in order to have thermodynamics and statistical mechanics respected properly. And over here you see a simple solid. I think this might be a manganese oxide or something like that, where you see the entropy, the energy, and the specific heat computed in various ways. And one of the things that you know from diagrammatic perturbation theory is that if you have a self-consistent phi derivable theory, no matter how you compute these quantities, you're going to get the same number. That's very different from the non-self-consistent theories, for example, second-order perturbation theory or GW, where there's an uncertainty or an ambiguity in the correlation energy of a factor of 2 due to that non-self-consistent nature. All right, so with that, we have the theory, the solid theory of the 1960s, the computational muscle of AI and machine learning, and now we can actually do that for realistic solids. And we can look at, response functions, band structures. And what I show you here is the band structure of silicon as obtained in a self-consistent perturbation theory on a 6x6 lattice, 6x6x6 lattice with self-consistent GW. Yeah, well, that doesn't look very good. What you see here is that silicon is most likely an insulator. That's why you don't see anything over here. At the gamma point, there is a maximum of this band, somewhere between gamma and X, probably there's a minimum. So likely this thing has an indirect band gap. Probably there's some bands somewhere over here, but really you can't see that much. And the reason why this is so bad is really that what you're seeing here is a result of an analytic continuation. We have very nice Matsubara Green's functions. We want to have real frequency Green's functions so we can talk to the experimentalists. Getting from Matsubara to real frequency requires analytic continuation. In that analytic continuation, in traditional methods, uncertainties get exponentially amplified. And that is really, really detrimental to spectroscopy. So that was the status circa 2020 or so, just before the pandemic broke out. And I then had a very talented undergraduate student who wanted to spend some time in my lab, Johnny Fay, who spent some time looking at this in a little bit more detail. Now, the analytic continuation problem is that we have computed g of I omega n, the Matsubara-Green's function. We're interested in getting the spectral function. Spectral function is related to the imaginary part of the real frequency Green's function, and the real frequency Green's function is related via analytic continuation to the Matsubara-Green's function. So you see this integral relation here, and we can discretite this integral kernel and write g of I omega n is kernel of I omega n omega times g of omega, and we can then extract g of omega by just simply inverting that kernel. Turns out that kernel is very, very badly behaved, and it needs to be regularized. And if you do that naively by just using some sort of matrix inversion, you get basically just noise. If you do this with methods like maximum entropy, you get this very, very fuzzy, very broad and spectral function. Now, back in the pandemic, Jenny and I revisited this problem, and we tried to analyze these Green's functions and try to see whether there's a better way of understanding the physics of spectral functions and the analytic continuation problem. Let's, for that, just briefly revisit the layman representation of a Green's function in the complex plane. This here is a Green's function. It is given by 1 over the partition function. Partition function is a positive number, times the sum over all states in Fock space, a matrix element squared, an exponentially decaying energy term here, that is positive. This one's also positive, times 1 over z plus en minus em, where en and em are real numbers. If you stare at this long enough, you see that the stuff that is in here and in the numerator is actually always positive. And now if you analyze this for z equals x plus iy, and you look at it for y greater than 0, you find that this function is always negative, or always has a negative imaginary part in the upper half of the complex plane. So in other words, Green's functions are actually sort of funny functions. They have a negative imaginary part anywhere in the upper half of the complex plane. And it turns out that back in the 1920s, these functions were analyzed up to a minus sign, were analyzed very deeply in measure theory and in probability theory. And they were analyzed so much that they have a name. They're called Neven-Linna function after this mathematician, Rolf Neven-Linna, that analyzed these functions. And it actually turns out that after a Möbius transform of these functions to the unit circle, they can be mapped onto so-called Schur functions. Schur functions are one-to-one correspond to Neven-Linna functions, are functions that every time you apply them to a point in the interior of the unit circle, they contract you towards the center. And so, why am I showing this to you? Because back in 1918, Isai Schur, you see him over here, said that, well, if you give me a bunch of points in the interior of the unit disk, I can construct for you all possible contractive functions, all possible Schur functions that are consistent with your points, that interpolate your points. And he didn't just say that, he actually gave a recursive interpolation algorithm that constructed a function space of all possible functions that can interpolate a given set of points. Now, this was long before computers, but it just so turns out that we can use the Schur algorithm to take Matsubara points, map them into the interior of the unit disk with Neven-Linna's mapping here, use Schur's recursive algorithm to construct all possible interpolants, use a mapping back, and now we have all possible Neven-Linna functions that are consistent with the original data. And that allows us to construct analytic continuation functions, not just by sort of approximately regularizing this with a smoothest possible function within some error bound, but to look at function spaces and do functional analysis in those function spaces to really analyze what are the legal functions that we have in this. Now, why is this interesting, or why do I show this to you? Well, it turns out that there are actually not that many functions that respect these properties, that they have to be strictly positive in the upper half of the complex plane or strictly negative in the upper half of the complex plane. Georg Pick, an Austrian mathematician who lived in the early part of the 20th century, analyzed the existence of Neven-Linna functions or Schur functions and said that, well, if you give me some points in the interior of the unit disk, you should do 1 minus the value times it at point I times the complex conjugate at point J divided by 1 minus location I times location J complex conjugate. Take that function or build that matrix for all the points that you have, diagonalize it, and it ought to be positive semi-definite. Now, if you just take a bunch of random points in the unit disk and you start evaluating matrices, you're going to get about as many positive as negative eigenvalues. And so what's sure here, or the pick here tells you, is that the criterion that you have to have a causal or a Nemann-Linna function is actually very restrictive. This function space is not very big. And so, if you have any data, you can straightforwardly check if it actually satisfies these criteria. And, you're going to get a function space, but that function space will be very constrained for actual problems. And that's the consequence of that. What you see on the left is what I showed you before. That was the status circa, 2020 of the spectral function of silicon. On the right, you see precisely the same input data, the same Matsubara data obtained with a self-consistent Matsubara field theory. In this case, GW on silicon 6x6x6. And all of a sudden you can see, yes, there is indeed a maximum at the gamma point. There's a triple degeneracy at the gamma point. There are individual bands that you can see dispersing over here. There is an indirect band gap between gamma and somewhere between gamma and X. There's this lobe over here that I'm sure you've seen in other places. And we can also resolve a couple of higher lying bands until finally we're actually losing resolution here. And the loss of that resolution really is the double precision information that we have that, we just don't have any better data. And this is still a very ill-posed analytic question. But that now is a major game changer, because all of a sudden we can now take finite temperature field theories and we can obtain optics response functions out of those finite temperature field theories in a reliable way. All right, I want to give a little bit of an aside here. Very often as you've heard in the introduction, I'm an old Monte Carlo person. And so very often we don't have exact Nemann-Linna functions, but only approximate Nemann-Linna functions. The data that we have in complex analysis, in complex analysis, if you know a function anywhere, you know it everywhere, right? If you wiggle your function a tiny little bit, you're going to change it everywhere. And so we only have data that is accurate up to about 14 digits at most, typically only to about 8 digits. And so Nemann-Linna continuation is very sensitive to noise because of that complex analysis route. Even semi-analytic data is only accurate to about 14 digits. And so often instead of having an interpolation algorithm, we actually want to have an approximation algorithm. And in particular, we want to have a controlled approximation, meaning that if we get more precise data, we're going to be able to resolve more, more features. And the traditional recipe that I've shown you before is that there are lots of functions, and we're just going to be taking the smoothest one that is consistent with the input data to within some error bar. My claim here is that we need a new regularization criterion. And rather than having the smoothest function, I want to have the function with the least information in it. Information in this context really consists of poles in the complex plane. And so I'm going to ask the question, every continued fraction expansion here, or every Nemann-Linna function has a continued fraction expansion. Every continued fraction expansion can be written as a pole expansion. That expansion doesn't need to terminate. But let's pick the pole expansion with the fewest pole that is consistent with the input data to within the given precision that we have our input data, and with any other analytic knowledge like moments or sum rules or things like that. Here's a typical pole representation. What you see here is a Green's function expressed as a sum over poles. The poles are expected to be discrete here. I'm going to look at the retarded Green's function, so I'm going to have my poles in the lower half of the complex plane. And I can truncate this at some value m, and the question is, how many m's do I need for typical spectral functions that we know and love? Here's a typical example. On the left, you see a tight binding of a 2D square lattice. On the right, you see a semicircular density of states. The left function here has 9 poles. The right one has 5 poles. And on the grid that I've approximated this on here, we have the function interpolated to, 10 to the minus 2. So percent. That's not too good, but it's also not too bad. But the point is that we can allow to have more points, and now we have 10 to the minus 4 precision, and we're getting 17 poles on one side, 11 on the other. 21 points and 13. You can see now we're at 10 to the minus 6 at the interpolation grid that I've used here. And so that's pretty, pretty accurate already. And of course we can, ramp this up and get progressively more and more accurate. Here's an epsilon of 10 to the minus 8 for the semicircular density of states. Yeah, and finally 10 to the minus 12. What do these functions look like, or what do these poles look like? Well, the exact solution of the semicircular density of states actually has a branch cut in the lower half of the complex plane. What you see is that those complex poles that we generated, they're basically glorified Lorentzians and anti-Lorentzians. You can see there's a subtle balance between the anti-Lorentzian over here and the Lorentzian over there, that when you add these different poles mimics the semicircular density of states. And rather than having a continuous branch cut in the lower half of the complex plane, we actually have a set of discrete poles that now approximate that function. As we ramp up the number of m here, we're going to model that branch cut better and better, and we're going to get more and more poles in the lower half of the complex plane. How do we do that? Well, constructing pole approximations is actually a very difficult or very interesting problem that has a lot of sort of interesting mathematics and complex analysis in it. Given a bunch of Matsubara point, our task is to construct a real frequency spectral function given by poles in the lower half of the complex plane. So the first we're going to do is we're going to construct a smooth approximant of that function along the imaginary axis. And we're going to do that with an exponential approximation, a so-called Prony approximation. This here is a Prony problem. Given our data, we're going to approximate our function with omega I, gamma I to the k, where the gamma I to the k are basically exponentially decaying functions. We then use a Zhukovsky transform to take the imaginary axis and map it onto the unit circle. That will take the poles on the real axis and will map the poles on the real axis onto this egg-shaped region that we have in the lower half of the complex plane, and it will take infinity and map it to 0. The moment we have that, we will do integrals across the boundary and calculate the moments of the function around the unit circle. All of the poles are inside the unit circle, so the moments actually decay very quickly. We can evaluate this numerically because we have a very good approximation of what the g of omega is, because we just had an exponential approximation constructed for it. Now we apply the residue theorem, and this really is just the only theorem you need to remember from complex analysis. Applying the residue theorem will give us the sum of the poles here, and will tell us that the moments that we've just constructed are pole weight times exponential or pole location to the power of k. That here, of course, is again a Prony problem. It's a second Prony problem, so if we solve this first Prony problem, we can solve this one too, and that will allow us to, with an inverse Zhukovsky transform, get the original poles and weights back. Now, what I haven't told you yet is how we actually solve the two exponential approximations that I have here, the two Prony problems. But it actually turns out that finding an approximation to a uniformly sampled function where you have a sum of sampled functions modeled by a bunch of pole weights and then oscillatory functions, that is a very, very old problem from signal processing. It's known as the Prony approximation problem, and it appears in acoustics where GK is a sampling of acoustic signal, for example, a microphone signal, and the omega i's are the strength of different frequencies, the gamma I to the k's model the frequencies at which this is oscillating. It is also the direction of arrival problem in radar. It is used, it's basically underlying mathematics to the phased array radar, the synthetic aperture radar, to sonar problems and things like that. And so that means that as an established signal processing problem, there is a very large literature and very well established numerical algorithms for solving that type of problem. And so we now can take the Matsubara analytic continuation problem and construct a Prony approximation problem to find the poles, pole strengths and pole locations of our analytic coordination problem. And you see a typical problem over here. Here is a spectral function that just consists of 2 poles. And we're asking the Prony approximation problem to please extract all the information that is in that spectral function on the Matsubara axis. If we give very inaccurate data, then it will tell us, well, there are 2 poles and they're sort of right, not quite. But as we ramp up the precision on the Matsubara axis, you can see that we will still get 2 sharp features, 2 poles, all the way until we have these features very, very well resolved. That's actually very different from traditional methods like maximum entropy, where if you have sharp excitation data, you will get this broadened, smoothened spectral function that is sort of consistent with the first moments of those of that distribution. We can also give something a little bit more complicated. Here you see a spectral function consisting actually of a bunch of Gaussians, below and above the Fermi energy over here. This is a sharp, let's call it quasi-particle peak. This is a feature behind it. If we feed this algorithm data that is relatively imprecise, it says, well, there's sort of 3 features there. And I'm going to give you 3, generalized Lorentzians, poles here back to model this approximately. And you really don't have more information than that. As we ramp up the precision of our data here, we're also getting back a gradually more and more precise resolution of what our spectral function is, and that allows us, eventually, resolving Gaussians with Lorentzians is a difficult problem, right? Eventually it tells us, well, you need at least 11 poles to model that function on the complex plane appropriately. All right, now this is actually an interesting problem also in a different respect, because the same type of functional analysis that gave us this type of Prony analysis can be used to analyze Green's functions in real time. And at the very beginning, I talked about Keldysh diagrammatic and Keldysh, sort of real-time Green's functions that you have after an excitation or a pump or a probe. And so here you see actually experimental data that models time-dependent response function. This is a magnetic response function, sorry. It's a magnetic response function over here. This is actually a pump probe signal, a 2-time signal, and a cut through that 2-time signal. That over here is a signal from second harmonic generation that models a charge response. And all of these are response function that sort of, wiggle. Now, we know that corresponding to this function is a response function that has to be causal. And the same causal structure implies that its Fourier transform is a so-called positive definite function. And those positive definite functions with the same type of analysis, same type of approximation, allow us to take experimental measurement data and reduce noise from it that is not consistent with that mathematical structure. Over here, you see, for example, a very extreme example. This is a Su-Schrieffer-Heeger model. It's actually modeled on a quantum computer. And on that quantum computer, you see that there is a computed real-time Green's function, or real-time response function. The data in real time actually looks like this. The Fourier transform, the spectral function of that data, looks like that. And you can see that this data has problem. On one hand, we know that there are just 2 sharp excitations, one here and one there. And clearly that data, well, doesn't get either one of those. Well, maybe it gets this one, but the other one is sort of negative and flipped. And then also there's a whole bunch of additional data that is about as much positive as negative rather than strictly positive. And so that just shows you that this is data that has been polluted with a lot of noise. And the physical signal, if there is any physical signal underneath it, is really hidden by that unphysical noise. Now, because these are Neven-Lina functions and their Fourier transform are positive definite functions, we can ask, well, what is the closest positive definite response function to this type of raw data? And we actually end up with this data. That doesn't look like it's the same data, but it's actually just a projection of the noisy data onto the closest positive definite function. And so down here you see a positive definite denoised function of this here. This is just the Fourier transform of that denoised data. And now all of a sudden you can see that there's still negative contributions, but now we actually see precisely where those spectral functions are, and we can really extract the excitations from that. It's of course still not perfect, because you see that there is positive signal over here, things get a little bit negative over here and over here. And the negative part of this has to do with the truncation of that Fourier transform after a given interval. But very closely related to that positivity problem are actually extension theorems. There is an extension theorem by Crane, and there's another one by Carathéodory, that says that if you have a positive semi-definite function that you know for some time, there is an extension. There may be infinitely many extensions, but there is at least one extension of that function for all times. Over here, you see the original raw data. Here you see the denoise data that I just showed you. And now just by enforcing the mathematical structure of positive definiteness, or the Neven-Linna structure of these Green's function, we can take the orange data and use the extension theorems to predict the orange data for much, much longer times. And if we do that, then all of a sudden you can see that there are two very sharp excitations in that problem. The function is majorly positive now. There are some spurious excitations still in the data, but those are physical excitations, or excitations, consistent with a physical direction in that space. And if we wanted to get rid of them, we would have to simulate cleaner data, or simulate for much longer. But so this mathematical structure now allows you to really take complex analysis of the 1920s and feed it through modern numerical techniques like radar techniques and so on to get quantum data that is very, very high precision, that would be much better than what you could just get with sort of brute force numerics. As an aside, one of the funny things here is that my undergraduate student here really didn't know how to do research. So she didn't know that it's not normal that you have to read papers from the 19-teens. And so, some of these papers are not in English. This one here, when we started from Schur, is in German. And you can see that, that is actually something that we can do nowadays with, simply running these papers through Google Translate. Gets a little bit more difficult when you get to the 1940s. This is Mr. Crane here, who was publishing in the Academy of the Soviet Union. And back in the 1940s, the language changed from German to, well, something else. And it had to be French in the 1940s. Still possible for me to read because I took French in high school. But some of the later papers, really present a challenge for reading this. And so we had to work with OCR and with LaTeX tech recognition that actually was able to read these papers and then translate it into LaTeX so that Google Translate could take this and translate some of these papers. So that was quite a journey. Anyway, I want to leave sort of this aside about analytic continuation and go back to modeling real materials physics with some of these numerical algorithms. Actually turns out that for a lot of the systems that we're interested in, relativistic effects are almost as important as correlation effects. And so, when we want to do spin orbit coupling or relativistic effects in calculations, the standard way that this is done is basically you do a non-relativistic calculation and then you manually add an L.S term into your calculation to get some sort of spin orbit coupling. But spin orbit coupling emerges ab initio from the solution of the Dirac equation rather than the Schrödinger equation. So that means we have to do it, if we want to do it right, we have to do it with electrons and positrons in the same calculation. And so physics, the theory of relativistic quantum electrodynamics is of course well known, but it's not in a form where one can easily do calculations for real materials with that theory. But there are recent developments in quantum chemistry where you can use the exact two-component relativistic approach. That is basically a formalism. Two components here means two spins of electrons, where you integrate out the higher energy degrees of freedom. There's then an approximation that is fairly powerful, which is x to c1e, where the two-body integrals remain non-relativistic and only the propagators of the one-body integrals become relativistic, which for us is perfect because the two-body integrals are those 405 terabyte files of two-body calculations. The one-body propagators are just our Green's function. And generalizing this to relativistic systems is then basically very similar to generalizing this to basic antiferromagnetic systems. Now, With that formalism that we've implemented, we can now look at spin-orbit coupled materials. Here is silver iodide, a typical spin-orbit coupled materials. This is it with a non-relativistic calculation. You can see that there are here and here degenerate bands. And of course, without the analytic continuation formalism that I've shown to you previously, there would be really no chance that we would ever be able to resolve the physics of this. But as we're then going to here, the relativistic formalism, you can see that some of these degeneracies are lifted, the bands are splitting, and now you see a very nice spin-orbit coupled system that really has bands of one spin different from the bands of the other spin. And with that, we can now do weakly coupled relativistic systems, absolutely parameter-free at finite temperature with, I would say, rigorous diagrammatic or finite temperature field theory formalism that is consistent and conserving and sort of very, very much textbook-like. The way that if you open a many-body textbook and you look at diagrams and propagators and so on, those are really the objects that we're talking about here. That's just half the story. Because now we know how to do weak coupling, but if you look at the periodic table up here, right, a lot of the stuff that we're interested in is in the lower part. And almost, by definition, you're not just getting relativistics, you're also getting strong correlations. And so you really have to go beyond weak coupling. So what do? Now, any, sort of first knee-jerk instinct has to be that you add a vertex correction. And, if you think about, a little bit more about this, then you see that this is not a good way forward. It may be a very good way if you have precise results for a semiconductor and you want to have even more precise results. Well, sure, right? Vertex corrections, when you have a small parameter, it will give you one more order or whatever, and it will give you a better result. But if you're already in a regime where you're outside of weak coupling, then adding just more weak coupling, one more weak coupling term is really not going to help you that much. You could also try to add fluctuation channels. Your traditionally trained analytic condensed matter theorists will usually go that route. We say, well, this is a system that will go superconducting, so let's add a superconducting ladder to that. Or this is a system that goes, magnetic, let's add a magnetic ladder to that. Or I expect a charge instability, let me add RPA diagrams. You can do that. What I'll show you in a bit is, even though you can do that, and those are, we have a couple approximations here that consider even all the fluctuations. That's usually quantitatively not a good way of going forward and thinking about the problem. What works is strong correlation embedding. In embedding theories, you basically take one of the orbitals out, or a bunch of the orbitals, an entire orbital subspace, and you say, well, on this orbital subspace, I need to have strong correlation. In the rest of my system, I'm going to be able to get away with just basically perturbative weak coupling corrections. So there are various ways you can do strong correlation embedding. Ideally, what you would like to do is renormalize your propagators and interactions, and then in that subspace, work with non-perturbative renormalized interactions and propagators. That's the so-called psi-functional or Almblatt psi-functional formalism. You can write this down. It's theoretically very beautiful, but there's a problem. This results in impurity problems that capture the strong correlation effects of these non-perturbative theories. And so far, nobody's been able to write an impurity solver that does general retarded interactions and propagators for realistic systems. We have some for model systems with density-density interactions, but not for the generic case that we would need in this case. And that's actually a major limitation that stops us from using this, very beautiful formalism. You can then say, oh, well, I don't care. I'm just going to truncate some of the orbital structure, or, I kick out all the terms that are not density-density, or I take my frequency-dependent interaction and just take the zero frequency limit. And I mean, sure, you can do that, but you're right back to sort of uncontrolled approximation territory, and then you have to justify why you're doing this. And you also have trouble, with, for example, statistical mechanics properties that don't quite work out, and ambiguities in definition of the energies, and so on. You can try and stick at the level of the phi functionals, and if you try to do that, The phi functionals are functionals where you have the bare interactions and renormalized propagators. If you try to do that, you are stuck with the electronic structure integrals, the bare integrals which go over very, very large energy scales and large temperature. And so you need to learn how to deal with extremely large energy scales if you want to go that way. But it turns out that numerics is quite good at dealing, adaptively with large energy scales. And so after a little bit of adaptive grids in numerical mathematics, we've actually figured out now how to do calculations like this, where you have a non-perturbative embedding that is fully ab initio, so it does not have any sort of renormalized interactions or downfoldings or things like that, and thereby becomes, predictive. We go back to the fluctuation route, right? If you go the standard analytic route and you talk about, adding fluctuations to the problem, you can ask, what is the type of fluctuations that I can add without resorting to a vertex function? If I go for a vertex function, typically the vertex functions will have multiple functions of frequency and multiple k indices and lots of orbital indices. And in a realistic problem, that's just too difficult to store or even manipulate. In a perturbative calculation where you can only afford one frequency, one momentum, and a bunch of orbital indices, the best you can do is add either GW diagrams or RPA diagrams, add T-matrix diagrams, so magnetic ladders or superconducting ladders, or if you're really sort of into it, you can add magnetic, superconducting, and charge fluctuations all together in one sort of expression, and you end up with the so-called fluctuation exchange theory. Here's an example of the three-dimensional Hubbard model looked at in these theories. It's the simplest fermionic model that has a phase transition where we know the exact result or a numerically exact result from QMC, and we can just simply ask, for relatively weak interactions, just barely outside of weak coupling, the full bandwidth is 12 in this model, right? So half of the full bandwidth for the interaction. How well do these methods actually work, like quantitatively? Let's start with charge fluctuations, fully self-consistent GW. What I have here is the it's the magnetic susceptibility as a function of temperature. We know the system has a phase transition. The phase transition is down here. GW will give you a phase transition. From the high temperature limit, the isotropic phase, I can actually measure the susceptibility and just extrapolate to over here. We're about off by, 20%, 30%, something like that. Not too bad. There's an ordered phase, right? We can also come from the ordered phase. This is a second order phase transition. This is like textbook phase transition physics, beautifully consistent, off by 30%. But, then again, this is a first order approximation. We're missing second order exchange here. Like, what do you expect? We can go to self-consistent second order perturbation theory. If you come from the isotropic phase, from the high temperature phase, the extrapolated phase transition is probably somewhere down here. It's not much better. It's also not much worse. You don't have an infinite number of diagrams, so there's nothing to diverge. So rather than having a second order phase transition, you're getting instead a first order jump. That first order jump is actually over here. So it's about as bad as GW, but you get first order instead of second order physics. We can then ask about the ladder. And this is a magnetic phase transition, so let's add the magnetic ladder. Here is the result from the magnetic ladder. You can see the magnetic ladder really loves to make this stuff magnetic. Surprisingly, it also has a first order phase transition, so you wouldn't want to try and extrapolate the phase transition temperature from high temperature by just following the susceptibility. And you're quite a bit off actually. But you can say, okay, fine, I only added magnetic diagrams and the system's magnetic, so I'm overestimating the phase transition. So, that's not that unusual. If you add the superconducting ladder instead, no phase transition. Okay. I mean, there's no superconductivity in this model, but it is a little bit disconcerting how these things jump. And finally, you can combine all of these, and rather surprisingly, you do find a first order phase transition. It's somewhere over here. It's not too far from the actual phase transition point. We actually can converge these results at the phase transition point. But one of the lessons that you get from this is that all of these diagrammatic resummations or partial summations of certain channels lead to a very unsystematic, difficult to converge result. Now, it's very hard to make sense of this in practice when you have a realistic system with lots of channels, lots of possible orders, lots of this here is really driving without seatbelts. So, I want to talk very briefly about quantum embedding. I think I'm basically out of time as an alternative route to all of this. The type of embedding that we've pioneered here is self-energy embedding theory, where we take an interacting solid, we solve the solid in a weak coupling formalism. We then, based on chemical intuition, decide that there should be strong correlations on some of these orbitals. We isolate the orbital subspaces in which we suspect that there may be strong correlations, and we solve them non-perturbatively. And then using, phi derivable diagrammatic field theory methods, we embed the strong correlation solution back into the weak correlation subspace and dynamically adjust those subspaces until we have a self-consistent solution of the weak coupling, strong coupling problem. This is very similar to dynamical mean field theory, only that in dynamical mean field theory, usually the interactions that you're working with come from, are adjusted dynamically, and the double counting terms are adjusted dynamically. If you remain, or what should I say here, right? In that formalism, the strongly correlated subspace is solved as a quantum impurity model. That quantum impurity model talks to the remainder of the system via a hybridization function that contains a retardation effect. And as long as we're sticking to a phi derivable formalism, we're actually sticking to the bare interactions, which we know from just the electronic structure problem. At the end of the day, we have an approximation to the Luttinger-Ward functional, which is consistent and conserving. It consists of the exact Luttinger-Ward functional in which we have kicked out all of the diagrams beyond GW in the orbital subspaces that are not strongly correlated. We can then approach the exact limit, at least in theory, by ramping up the diagrammatic order in the weak coupling subspace, or by enlarging the strongly correlated subspace until all of the diagrams are included in that. And the cool thing about all of this is that it's fully ab initio. We choose the basis, we choose the methodology, GW, for example, and strong correlation, and we choose the correlated subspace. But at that point, that's it for our problem, right? There's now one self-consistent solution which has the lowest free energy, and the numerical machinery here just has to find that numerical solution. How does this actually work in practice? What you see here is self-consistent GW for strontium manganate. Strontium manganate is a perovskite insulating material. Within GW, you can see that clearly this thing is metallic. So it has density of states at the Fermi energy. And the metallic character here comes both from the manganese T2Gs and from the oxygen Ps. As we look at the solution, we can suspect that the manganese T2Gs probably have strong correlations on them, and non-perturbative contributions are going to be important. So by adding those strong correlations and going to a non-perturbative solution of the manganese T2G subspace, we're starting to open a gap. We're splitting these orbitals, and you can see that we're both adjusting the manganese T2Gs, but we're also adjusting the oxygen Ps, which in this calculation are still weakly correlated. So it's the correspondence between the strongly correlated subspace and the weakly correlated background via the phi functional, that adjusts this propagator and makes this an insulator. And then finally, we can suspect that there may be additionally strongly correlated subspaces. For example, the manganese EGs. They're a little bit away from the Fermi surface, but we can just try to add them to a quantum impurity problem. As we're doing this, you find that there's really not that much change to any of this. And you're basically sticking with a solution that is basically now robust to adding the impurity subspace. And so that's a poor man's convergence of this sort of correlation hierarchy. If this works for strongly correlated insulators, how does it work for strongly correlated metals? Well, this was the strontium manganese that I just showed to you. This here is the strontium vanadate. If we look at strontium vanadate in self-consistent GW, it is actually a boring metal that has, some wiggles near the Fermi surface, but not really a quasi-particle peak. As we are starting to add the vanadium T2Gs to the strongly correlated subspace, we're starting to see strong correlation metallic physics. This is now a quasi-particle peak that is emerging here due to correlations, really a cousin of the Kondo peak in this particular system. And then as we're ramping up the correlation degrees, again, you see that there's really not that much change to that. Again, showing that for these very simple cubic perovskites, we can actually converge, this correlation hierarchy. And so really, that is the goal, right? There's the idea or the dream here that you can have numerics of strongly correlated quantum systems in a sort of convergent and controlled way. As you're going up that ladder, you're going to have to pay for it. There's more and more, correlations you need to consider. There's more and more, impurity problems that you need to solve, or larger and larger impurity problems. Every additional step adds complexity, but it gets you closer to the exact results. And so really, that's something that is in a way new to quantum mechanics, but it's very well known in other fields of science. What you see over here is, for example, finite element of, in this case, a dielectric breakthrough simulation. And you can see that far away from where it is interesting, you're solving this problem at a very coarse sort of picture. In this case, it's a coarse discretization. In our case, it would just be a weak coupling solution. As you're getting towards the strongly correlated subspace and the sort of strongly correlated, physics, you're going to have to ramp up the correlation degree. You're going to have to go non-perturbative, add higher order terms and so on. And, eventually you'll be able to resolve these systems. And how you do that in practice for our type of, quantum systems, that's a big open question, because we have lots of different control parameters that we need to account for in practice. Right, so system size is an obvious one, right? You go from a 4x4x4 to a 6x6x6 to an 8x8x8 lattice. Is it big enough or not, right? Then there's diagram types, right? Certain diagrams should be valid, certain diagrams you like. There's diagram order, there's entanglement types. There's the embedding subspace that you're using for the strongly correlated system. There's the basis set that you're using to capture your electronic structure system. That's actually a very underappreciated problem in our sort of community, right? And sort of as you go up those hierarchies and you try to converge these, ideally you'll be able to show that you are now converged in this hierarchy and you've really captured the problem to the precision that you care about for this particular problem. Anyway, so where do we stand? I would say that we have a solid foundation to perform many-body theory ab initio without adjustable parameters, reproducibly and accurately. We can really now do what the guys wrote down in the 1960s, on a piece of paper, which is, correct in principle, but doing an actual calculation with this was basically impossible until, very, very recently. The leading error in these calculations, or a lot of these calculations, actually the weak coupling approximation. All of the other approximations are either eliminated or actually fairly well under control. We can do relativistic systems. We can do excitations, and getting to the excitations required us to revisit, complex analysis of the 1920s, which is a little bit of a side quest, but actually, absolutely essential for getting, reliable results for any of these things. Just going and increasing diagram order is not the right way, at least for these systems. We can do it technically, but it seems it's just not a very well controlled way of doing it. The embedding approach works very well, works well in models where we've known this for years, but it actually can be adjusted to realistic systems in practice. It is technically difficult to do. It needs a lot of a sort of numerical backend, and I haven't talked about any of this in this talk, but all of that numerical backend is improving very, very rapidly. And so it provides a non-perturbative component to solving all of these problems. With this, we have experimental connections at our fingertip. We can really go down to the labs and show, hey, look, this is, nickel oxide or strontium vanadate or strontium manganate or chromium sulfur bromide or whatever. And this is what one would expect to measure in angle resolved photo emission spectroscopy. And with this, we have experimental connections at our fingertips. But still, there's a very long way to go to sort of routine parameter-free ab initio calculations, the same way that DFT people do it, where this is really a toolkit available for undergrads, and it's actually sort of easy to get good results out of it. For strong correlations, we're just not there yet, but there is a road to that future. And so with that, I want to thank my group members, in particular Gianni, who did all of the analytic continuation stuff, Janan, who did the adaptation to GPUs, Sergey, who did a lot of the real materials coding, Domenica, who was involved in almost all of these projects and did the relativistics, and Lei over here, who was doing the pole expansion and pole approximation stuff. As I've mentioned before, I will be in Warsaw for the next 5 years, and I have PhD positions and postdoc positions over there. And I would like to thank you very much for your attention.
Thank you very much, Emanuel, for an interesting talk. And I think we can move to questions and answers session. So we are open now. Yes, Sergey, please start.
Well, you're in a couple of slides you advertised using GPU instead of CPU. This in some calculations this can make supercomputers out of our PCs. Can you tell about your experience in particular and your understanding in general? When is this beneficial?
So there's really one reason why this works well here. Let me see if I can pull this up again. I have, if you look at these diagrams, right, these are contractions between interactions and propagators. And basically the propagators are matrices, they have, or tensors, they have orbital I, orbital J, momentum K, and imaginary time tau, so it's a rank 4 tensor. The interactions are V, I, J, K, L, K, K prime Q, right? So basically these are high dimensional tensors, and what I've written here is a glorified matrix contraction or tensor contraction. The moment you can write your problem as a sequence of lots of tensor contractions, GPUs are fantastic. They are really bad at doing Monte Carlo or any sort of logic decision. And they're really good at doing parallel matrix multiplies. So step number one is basically rewriting what you're having as a set of lots of independent matrix multiplies of a reasonably small dimension. Reasonably small dimension is important because the streaming multiprocessors that you have on these things, this basically, on CPUs you would have multiple cores. On these things, you have multiple streaming processors that can independently work on some of these matrix multiplication tasks. And so you're converting a contraction of tensors into basically a dispatch of lots of independent matrix multiplies. As long as you can formulate your problem like that, GPUs are fantastic.
Yeah, thank you. And I think that we can see more on this paper at the bottom.
Yes. So I think that there's this paper. There's also a follow-up paper that actually has the algorithms and has the open source code that does the GPU contraction with like scaling and timing and things like that.
Thank you.
So from my side, I would like to thank additionally for pointing out the Zhukovsky transform. When I was studying at university, I was thinking that it's only applicable to aerodynamics applications, which were not state-of-the-art at that point, but now it's even in condensed matter physics.
Yeah,
that's great.
The Zhukovsky transform is famous for being useless. But and sort of for being stuffy old stuff, right? I mean, it's I would say sort of more globally, there's the numerics approach of just we take a problem, we discretize it, we throw it on a computer, and then we just let it go brr. And there's the numerics approach of we do the analytics as far as we can get, and then the rest we do with mathematics, with basically brute force numerics, and finding the right way of using the analytics to your advantage to make the computation go right. That's really that's in a way the skill, right? That's where you're aiming. And just going like take maximum entropy analytic continuation, right? I mean, for years, analytic continuation was considered just a dead field. Like, you should not do finite temperature stuff if you want to have precise spectral function.
Right.
No amount of GPUs is going to help you with that. But it is really, mathematics, and in this case, a combination of like 1920s, complex analysis, of operator theory that, by the way, has a big Ukrainian community that is still doing this stuff, and of radar numerics. And it's actually funny that the Esprit guys, so the radar guys that are doing phased array radars, they've never heard of basically the underlying complex analysis structure. They're just not thinking about it in that way. They're thinking about noise and covariance matrices and sort of a statistical approach. But by making these connections, sort of, you're opening a way of doing the numerics cleverly. And that's really what's needed here.
Yeah, that's a wonderful strategy, I would say. So, and I have a question regarding your slides on the quantum computing. I think you were asked before, but could you comment whether it could be applicable for error correction purposes, which is very popular now?
Yes. So when we talk about error corrections on quantum computers, typically what people talk about is totally problem agnostic, right? I mean, it's really trying to figure out what the cross correlations are on your qubit and then finding clever ways of getting rid of it. This here is a little bit different. Basically, you as a quantum computing practitioner, you go and use your best quantum computer, and this here is IBM Auckland. At the time, this was newest and best and really, state of the art of what one could do. And the results look disappointing, right? But that's the best that you can do on these machines. And so, basically that's the end of it. At the end of it, that's the result that you're having. And then you do mathematics. And the mathematics that underlies this is a correspondence. It's basically Bochner's theorem. We know that the spectral function is a positive function. And we know that the Fourier transform of a positive function is a positive definite function. Okay? It's basically a function where when you evaluate it at any arbitrary points and you build the Gramian, the matrix between those, and you diagonalize that matrix, it has to be positive semi-definite, same way that Pick had it for you, right? So that's domain knowledge, right? I don't need to know anything about your quantum computer. I need to know that what you were measuring was a Fourier transform of a positive function. Mm-hmm. And so that additional knowledge will introduce cross correlations between different time points. And so when what's really happening here is you have errors as a function of time, but those errors are independent, right? Different errors at different times come from different quantum simulations. By denoising it in this way, we're introducing cross correlations. Basically, results that you measured at short times constrain results that you measure at long time. That's the mathematics of having a positive Fourier transform, right? As a positive definite function. And so it's not universally applicable denoising, but it's domain-specific knowledge about the mathematics that you're expecting for the function that you're measuring that allows you to project this out and help denoising these functions. And so in a way, it's extremely powerful, but it's also limited to that type of physics application.
Right. Yeah. Thank you. And if I may, I have one more question about self-energy embedding theory. So do you have some estimates how well it performs, for example, with the increase of coordination number? So does it perform better like DMFT, or it's different kind of scaling or behavior?
Yeah, I mean, all of this is for realistic solids. So there's no easy way for us to change the coordination number. I mean, coordination number is just whatever it is. Mm-hmm. It's also the orbitals that we're using in here are not atomic orbitals, right? they're basically, localized orbitals, that are close to the Fermi energy, but they don't have to correspond to, an orbital of a given atom. In fact, there isn't even such a thing, right? I mean, once you have a solid, all of these things become linearly dependent eventually, and you're talking about linear combinations of atomic orbitals anyway that live in a certain irrep of your space group. And so the best that we can do here is look at a couple of systems that that we have and sort of try and establish how well this works in practice. But there's no way that we can go, for example, beyond the local limit because it's just too expensive. There's also no way in which we can go beyond, currently about 3 orbitals for the embedding subspace. So basically, we don't know. We can compare to experiment, but if you look at, let me see if I can pull up one of these experiments over here, right? So for example, here you have X-ray absorption spectroscopy and photoemission. So this is Bremsstrahlung, this is photoemission. And, at first glance, it looks absolutely, sort of terrible, because the different peak heights don't line up, the gap sizes don't match. But then you realize, well, these are actually different experiments that have different zeros. So you can arbitrarily shift orange with black. And then there are matrix elements that are, will give you different sensitivity for some orbital versus some other orbital. So for example, this oxygen P peak and this, this different peak that you have from, this different peak that you have from over here, they don't have to have the same height because they have different matrix elements for it. So the comparison to experiment is very, very tricky, and we really don't know how to have that comparison. And ideally, we would like to have a theory that gives not just its number, but some sort of error bar. And so the closest you can see for that is, sort of these things over here. I didn't go into this in detail, but as we enlarge the impurity size, right, we know that eventually if we had everything strongly correlated, we'd be exact. Best we can do here is we can enlarge, we can add a couple additional impurities and just show that there are no strong correlations there. And that's basically what happens in these various things. But, there's no exact solution for any of this. There's no infinite coordination number limit that you can appeal to. You can take these things and stretch them and squish them. And you can do that in experiment too. And as you see in condensed matter, we think that, as you go to large U, you're going over a strong correlation phase transition. But, if you go to an actual realistic solid and you squish it, then you go to a weak coupling system. As you stretch it, you go to a strong correlation limit. That's basically changing the interaction to hopping ratio. And in that way, you can actually, in certain compounds, you can actually really do that. And here we can see how our calculations change as we try to mimic that. Again, not as good as you would want it to be.
I see. Thank you for a comprehensive answer. So we do not have questions, but we have a comment in chat. So let me read it. Thank you, Emanuel, for your confident style and comfortable speed of presentation. It's nice to receive information in a powerful, continuous flow. Keep it up. So I think this is very correct comment. So yeah, we enjoyed your presentation a lot and the amount of information as well.
Thank you very much.
Thank you.
Thank you. So with this, I would like to finish our seminar. And so all the best on your new place in Warsaw, and hope to see you in person next time as well.
All right. Gladly. All right. Thank you very much for hosting me, and have a nice day.
Thank you. Bye-bye.